some methods of how we can do this. So to talk briefly about the data, we can technically, oh, I didn't see that. Okay, so we can technically categorize our data, the measurements of the brain into two main categories. One of them is we say, oh, we are measuring the structure properties of the brain, and we can use many modalities, many type of scanners to do that. For example, we can use CT scan, we can use MRI machines to do that, and then using different modalities of MRI, we can capture different aspects of that structure, or we can measure a function of the brain, right? We can say, oh, this part of the brain function like this, and that part function like that. And then again, there are many methods that we can use. EEG is one of the famous ones, and there is PET, and there is fMRI. In this talk, I focus, most of the data that I talk about is based on fMRI. There are fMRI, right, functional magnetic resonance imaging, which is an indirect measure of activity, right? And it's a but the tools that I talk about usually can be used on other functional data too. So it doesn't really matter. But the data that I talk about is fMRI here. So as I mentioned, we want to construct the network, right? We can break that step into two steps. Sometimes we do these two steps together, or the sequence of them are different. But there are essentially two steps. The first one is we have to find the nodes, the functional units of that system that we want to represent the data, to build a representation of, right? So we have to get the nodes of that network that we want to construct. Then we have to estimate a relationship between those nodes, right? Which are called edges, for example, in network science. And as I mentioned in our work in neuroimaging, especially, we use connectivity. The term connectivity all the time. We say, oh, this is connectivity. That means that, oh, this is just the edges of between the nodes, the functional units of that network. We want to do this too, right? So for the first part, there are many methods again, right? If I can break them, there are methods that are based on ROIs. And technically, they mean that we use atlases, for example, either using in vivo brain, for example, using actual brains to segment that brain into different parts, or using previous studies to break this brain into different parts. For example, say, oh, this part is like visual, this part is auditory, etc., etc. And we build the atlas, and we can construct our nodes using those atlases. Or we can use data-driven approaches that has garnered a lot of attention recently. For example, one of the more famous one uses independent component analysis that try to, without any prior knowledge, try to extract and estimate the nodes from the data. And in brain, each node usually has an associated spatial map to it and a functional time series to it, right? Which essentially says that, oh, this node come from these parts of the brain, right? And it come from these parts of the brain, and its function, whatever that is, it sometimes is a little confusing, but whatever that is, its function changes like this through time, right? So each node usually has a spatial map and a time series. And we can use these time series, we get these time series for the nodes, we can get these and calculate the connectivity, for example, here, pairwise connectivity between the nodes, right? Using the methods that I explained some of them. And that's how we can construct both the nodes and then estimate the connectivity between those nodes and therefore construct the network, right? Historically, we've been doing this in such a way that the connectivity was calculated across the whole temporal range of data, right? That means that we get the whole, these two time series, and we get one value for the whole thing, right? The connectivity of that network is constant throughout time. But here, as I mentioned, because the brain is dynamic and we want to capture that dynamism, we want the edges to change with time, the weight of the edges, the connections, to change with time. We want to be able to capture those. And here, so I talked about that we want to have a representation that change with time, right? That is a very broad purpose that we can have, and it can mean many things across the field, right? Because technically, even the nodes themselves can change with time. We have something that is attracting a lot of attention recently, like spatial dynamic, right? The nodes themselves change through time. But here I focus, and my focus as all my research is I essentially assume that the nodes are constant through time. So the nodes are constant, but I am trying to allow the edges to change with time. So one of the entities of the network is constant, which is the node. The other one, which are the edges, change with time. And usually in our lab, and what we really like to do is that we use actually a pipeline that uses ICA at its core to estimate the nodes from the fMRI data, which is a 4D image, right? fMRI data is a 4D. It's one volume at each time, right? It's a 4D. I'm not going to talk about it, but I just mentioned that we use it. But assume from here now that we have our data, fMRI data, we run ICA on it or whatever, and we get our nodes, right? So we have the nodes. Now the question is, how can we have a connectivity that changes with time? And the term that we use, there are many terms that is used, but the term that I like to use a lot, and I try to always advertise, is that time-resolved functional connectivity, right? Well, the term time-resolved makes sense because it's time-resolved, right? And the functional connectivity, because the data is functional, that connectivity is gives you an idea of the function of the brain. So because we can have a structural connectivity, but here we are working on functional data. That's why the connectivity is functional. So TRFC that you see here is all, when I will talk about it in the presentation, I mean that the edges changes with time, right? So a general pipeline, if we look at a general pipeline, it's not, of course, there are many ways to do it. It's way too many, right? And one of the general pipeline, but the general pipeline of a method that can use networks to analyze the human brain is something like that, right? So for example, we get the raw data from fMRI using MRI scanner, for example, right? And then we have to pre-process that. We pre-process the data. Then we, as I mentioned, we can extract the nodes using methods like, for example, here using group ICA. We call it group ICA, right? It's a method that uses ICA to get the nodes, right? And then that is estimating the node part of constructing the network. Then we can estimate the edges, which are used those time series. And after these two steps, we have the networks. But one issue that I'm not going to talk a lot about here, but it exists, is that it results in a lot of data, right? Which, of course, it makes sense, right? Because we have subjects, we have time, but we have to summarize it. You cannot just publish all of the networks, right? It just doesn't work. You have to summarize it in such a way that capture some of the aspects that we care about that network. So there are many methods to do that. A lot of them are based on network science. Usually here, I generally use k-means here, but because the focus here is mostly on this second part. But yeah, there are many ways to do that. For example, clustering approaches. There are many modularity detection approaches in networks, and etc. And finally, of course, you have to have a post-hoc analysis that we do, usually a statistical analysis, right? So that is the general pipeline of how we can how the whole analysis is usually done, right? So, and the focus here is the second step, right? Estimating the edges, the time-resolved functional connectivity. So there are actually many methods to do that, right? There are many methods to do that. They are actually estimating sometimes vastly different things, right? One thing that people always have to consider is that when we say connectivity, it's not a physical thing that we are estimating, that we are capturing. It can be anything that the researcher technically wants, right? And so there are actually different things that these different methods capture. So connectivity is, look at it as more of abstract notion of connection between different parts of the brain. What that connection is a whole another matter, right? So there are many methods here. One of them that is most famous, and it's actually used the most, is a sliding window Pearson correlation. The reason that it's used the most is, well, because Pearson correlation is a very well-known method. That's one of the main reasons, right? It's been 100 years, I don't know, maybe more, that it was developed, and it's very well-known. We know a lot of its properties, so this method is used a lot, right? And the method is quite simple, right? We have a sliding window that we slide through time, and at each window, we calculate Pearson correlation, right? That's it. That's the gist of it. Now, there are a lot of studies that play with the window shape or whatever, right? But the main part of it is just that a sliding window plus calculate correlation, sample Pearson correlation at each of those windows, right? This is one of the most well-known method. If you look at the studies, most of the studies use this. So it has two issues. I like them. I usually like to call them more of a feature, because to me it's like more a feature of the thing. But we can say, oh, these are the issues of the method, and these issues you can view them. It's easy to understand if we look at a sliding window Pearson correlation as a system, right? It's a system that it has its own subsystem, and if you look at it, it's actually very simple. It has technically 3 layers of system. The first one is a high pass filter. The second one is a coupling filter, and the last one is a low pass filter, right? It's just a combination of these. It's nothing fancy, right? Now, the issue that arises is that this high pass filter, if we do not select our parameter correctly, this high pass filter might remove important information of the activity signal, the X and Y, right? The node time set. It might remove those information. And this is really important for fMRI, because we know fMRI is a low frequency time series because of how it is, right? It's one of the properties of fMRI itself. So if we don't select our parameter correctly, we just remove stuff, and we are calculating correlation between noise technically, right? The other part of it comes from the last filter, which is a low pass filter. And the issue that it causes, if we select our window again incorrectly, if we choose the parameter incorrectly, we might smooth out important information, right? Because notice that connectivity is something that we are estimating. We actually do not know what property it should have. We can study some of the properties of the activities, the X and Y's, but the properties of the connectivity are unknown to us. So we do not know what information should be smoothed out and what it shouldn't smooth out. So it is actually really hard. So, and both of these issues are actually related to one parameter, or the whole thing, window shape and window size, right? So what we want, and what a lot of papers argue, is that we want a long window so that we don't filter out important information of the activity, and we want a short window so that we don't smooth out important information of the connectivity. But as you notice, these two are opposite of each other, right? We want two different things. We cannot have both, unfortunately, right? So in this project, I just in this talk, I talk a little about some of the methods that I come up with. There are kind of simple methods that I come up with to try to fix these two, address these two. It's not fix, address these two. So, and for the low pass part, as I mentioned, we are not sure if we are smoothing out important information of connectivity, right? For this, I said, okay, why not just a very simple solution was that why not just remove this low pass filter and put a filter bank there, right? That way, technically we can view connectivity across different filter banks, right? Of course, this has its own cost or whatever, but we are not going to talk about it. Let's ignore that, right? So, but technically, it allows us to view connectivity at different bands, so we are not losing information, right? And which might be good, right? So, and there are some other stuff how to design the filters. We can use some of the ideas in filter bank design for filter bank design, but let's pass that. So we can use this to look at a real fMRI data set, and the data set that I talk about here is a data set that has, I think, 300 subjects, and it has 2 groups: controls and schizophrenics, right? Individual with schizophrenia, which is a mental health disorder that our lab actually studies a lot. So it's a data set that has these 2, right? And as I mentioned, we use the group ICA toolbox to decompose the data into many components, nodes. And we can sometimes we group these nodes based on their spatial map into some functional domain. We call them functional domain, for example, visual, auditory, cognitive, etc. Right? It's just a visual thing that we do, just because we want them to be grouped together. And And yeah, as I mentioned, so and then we can use FPC, filter bank connectivity, to estimate connectivity across different filter banks, across different frequencies on the estimated on the nodes time series, and we use k-means to estimate the to summarize those estimation, right? And here we can use something like elbow criteria, for example, to find, oh, we just want to look at 8 cluster, right? 8 summarization, 8 means of that, the whole thing. And we have the good thing here is that because we are looking at different filter banks, right? We have a kind of a frequency profile for each state, right? And we can break our 8 cluster into 3 different groups based on their frequency profile, right? So for example, we have a low pass cluster, 3 cluster here. For example, you see the first line is the first row is the cluster centroid, right? Because it's a connectivity matrix, right? So it's a matrix of each, it's adjacency matrix technically, right? So each these are the cluster centroid. This is the frequency profile, which is based on fraction rate, right? How much the data exists in that specific state, and then we can average stuff to get a frequency profile. Or we can use the last row, or we can use look at the fraction rate and compare if the 2 groups are show significant difference for fraction rate, right? So so we can, for example, see here that schizophrenic stay more in this cluster 1, which shows a kind of a disconnected state, right? I'm not going to go deep into the clinical aspect of it, but these stuff are usually backed by literature. So we can see here that, oh, the schizophrenic stay more in a kind of disconnected state, right? And we see that the typical control stay in this state more, which shows a very strong modular pattern, right? It's known that controls have a more modular structure in their connectivity. And then we can look at the other 3 clusters that are show bandpass, right? If you look at the frequency profile, we see that they show a bandpass. They show a bandpass frequency profile, and here we see a similar result again. That typical control stay in this cluster. That is very similar to the modular state that we saw in the previous one, right? In the previous page, this one. This shows that this cluster is actually kind of bandpass. It's not a very low frequency connectivity, and this has its own interesting thing, right? Because this means that this is not only a static connectivity, it's actually go way above a static and way above time average, right? So, and then the last 2 states that show a very high frequency content, right? And this is here that things become a little sketchy, because although that we are looking at all frequency, there is still noise, right? We know SNR go lower as for higher frequencies, so we are not sure how noisy these estimations are, but here they are, and we see they show a kind of a less modular patterns, right? Which is which matches the literature previously, right? And we see that schizophrenic stay more in these cluster more too, right? So that was trying to solve one of the issues, right? And the other issue that I mentioned is that this high-pass filter might remove, filter out important information of the connectivity, right? How can we solve that, right? So they think that we had an idea. It's like, again, it's kind of a simple idea, is that, well, why not move information from the low frequency to high frequency in such a way that the connectivity in such a way that we can estimate the connectivity, the true connectivity, right? And to do that, we found that if we use single sideband modulation, it worked great, right? So what we are doing is just moving the stuff to higher frequency so that we are not worried about filtering out important information. And you guys probably know single sideband modulation is a kind of old method in communication theory, right? It's, I think, 60 years old at this point, right? And it's very simple, right? You just use, if this is your spectrum of your signal, you just use Fourier transform of your signal. You just use Hilbert transform to get the analytic signal, and then modulate it to another frequency here to higher frequency. And then by calculating the real part of that, you put back the opposite sideband to it, right? It's very simple to calculate, right? The good thing in this method is that it allows the signal to stay real, right? Which is a very good thing, because working with complex numbers is really hard, especially for networks and stat. It's a whole mess. So we really want stuff to stay real as much as possible, right? And so we actually can show mathematically, both mathematically and using synthesized data, that under a specific assumption, this thing that we added to a sliding window Pearson correlation does not change the power of the estimation, right? It actually increases, right? So, and we have shown that, right? And we can actually show using synthesized data that our method works very well, right? But that's not all. A lot of times what the field really wants, what other want, how can we show on real data to that your method works better, right? Because that's the end goal technically, right? And it's really hard because none of our synthesizers, none of our simulated data can capture the complexity of the brain. By this point, we do not have any simulation method that can capture even a fraction of the complexity of the brain, right? So it's really, a lot of people are looking for ways that we can compare methods on real data, but it's really hard, right? So we had an idea, we said, okay, it's really hard to say if this method, for example, or many other methods, right, can capture the connectivity, but technically, time result functional connectivity should have the information of the time average connectivity. And by time average connectivity, I mean, for example, if you use Pearson correlation using the whole temporal range of data, that information should be in PRFC, which is its average, actually, right? It's actually can be shown. And so if we calculate the MSE of the static functional connectivity calculated over the whole temporal range of the data with the average time result functional connectivity, right? Calculate time result functional connectivity and average it, these two should be closer. The closer they are, the better for us, right? So as I mentioned, if just get the 2 times calculate the correlation, Pearson correlation, or other estimator, and you have your static functional connectivity, right? And then use a method, for example, a sliding window Pearson correlation here to calculate PRFC and then average, right? We want these two, the lower is better here, right? And here we actually can see that the blue is classic SWPC, while the green is SSP plus SWPC. We see that, yeah, the method works better, although the power of the improvement is low, right? And it makes sense because these data are actually long, so it actually makes sense. But it's significant, right? At least. So we had another one in the paper that I'm gonna skip here that we show, okay, yeah, this method works better, right? So, and then again, we can apply it on real data. And here we get 5 cluster centroids. The reason that the number are different is because, well, elbow criteria returns different number. I mean, different methods. It's elbow criteria, right? It's very finicky. So, and here we get 5. It's actually the results are quite similar between SWPC and SSP plus SWPC, right? We see the same kind of pattern, right? For example, we see cluster 1 that is schizophrenic here. Again, the data set is based on a schizophrenic control. We see that schizophrenic show more disconnected state, while typical control show more modular state. The only difference is in cluster 4, right? This is the only difference that is here. And you cannot say that one cluster centroid is wrong, right? Because, well, we do not have ground truth, and we actually do not have any way to know the ground truth, right? But based on a lot of other studies and something, we actually accept to see something like this, to see this connectivity pattern. This is very similar to the bandpass connectivity pattern that we saw in filter bank connectivity. This one is a little different than this. If you look at it, the modularity is different. That's why there are 2 different clusters, right? And so we expect to see something like that based on literature, our own work, and other works that use other methods, right? We use wavelet, for example, we see that too. But this thing, this kind of pattern is less reported, right? It has actually been reported, but less reported. So I just leave you with that. I cannot really say which one is better, right? No one really can. And so, but this is the difference that these 2 methods find, right? Actually, we cannot see this cluster centroid at all, even if we increase the number of clusters using SSP plus SRE, right? So I tried these projects that I explained was my earlier work, my earlier PhD works. I tried to solve these 2 issues, kind of issues of SWPC, right? But there is another issue with SWPC that actually is a kind of a baked into it, right? And that issue is that SWPC can only, like Pearson correlation, like many other correlation methods, right, distant correlation, like Spearman, they can be used to construct pairwise networks, right? They can give you connectivity between pairs, right? They can go higher than that. It's just baked into them, right? And so, as I mentioned, we can build a network like that, like this, if you use SWPC or some other method, right? But what if we want to go higher? What if we want to build network that have that are higher order, right? And why do we want that, or is it even necessary for brain? So there are actually many reasons to do that, right? There are many literature on this. I just leave you with that we actually have shown that models that use high order network, we can observe explosive phenomena, right, easier in them, right? Explosive phenomena is something when we increase our control parameters, something explodes in the model, right? And in brain, we have these explosive phenomena in, for example, neural avalanches, right? The brain light up. It's not like light up, but you get my meaning. In data, you can see, oh, a lot of things are happening together, right? So there are many reasons for us to want to go higher, right? As I mentioned, these are for example, some of the neural avalanches that can happen in time very fast, right? Fast transitions. So one thing that we came up with, we said, okay, let's come up with a method that combine stuff, right? But let's come up with a unified method that it can combine stuff and can give us a high order network, right? And we use the idea of method of moments that is actually something that Pearson himself actually came up with. We combine the idea behind method of moments, a short-time Fourier transform, and SSV again, right? To give an estimation that estimator that can give us connectivity, that can help us to construct networks of any order that is resolved in both time and frequency, right? The three features that we want. So order, time, and frequency, right? And that order allows us to have, for example, nonlinear connectivity, right? It's like, I don't know, X to Y, right? We can have nonlinear connectivity. And the formula that we came up is like this. It's actually quite simple. It's I tend to like simple methods, right? It's very simple, and if we can break it, it has a kind of a Gaussian window, right? Which is like a Gaussian window in a short-time Fourier transform. And this function S is a function that is a SSV function, as I mentioned, right? Calculate the analytic signal and then multiply that by a modulation time series to modulate that. And this analytic signal is, of course, the ZT convolved with a filter to make sure that we don't have kind of aliasing effects, right? So the formula is like this, as I mentioned. It's quite simple, right? And the order come from here, the RJ, right? For example, if RJ is a vector 1, 1, this result in a time frequency version of Pearson correlation, right? If, for example, RJ is a scalar like 2, it become variance, right? And vice versa. So as I mentioned, it's a method of moments. You can estimate moments of different orders, right? Because Pearson correlation is a moment, right? It's a standardized moment. So the concept is, as I mentioned, is very simple. And the idea is that, oh, you calculate the standardized time series by passing it through a kind of a moving Z transform, right? And then you multiply stuff. For example, if you want pairwise, you multiply pairs. If you want triangles, you can multiply sets of 3, etc. You can go higher and higher and higher, right? And then you pass it through the last function, S function, and convolve it with that HT to get a time series of different. For example, this E is the pairwise connectivity, while this F is triangular connectivity or triwise connectivity, or it has a lot of names. I just forget to mention here that you cannot actually build this triangle using the 3 links, right? You cannot say, oh, I find the pairwise between 1, 2, 2, 3, and 1, 3, and pick that triangle, right? Get one value. It actually doesn't always work like that. It's under a specific assumption work like that. And that's why high order networks are important, because a lot of information, high order information, are lost if you only look at only pairwise, right? So that's the concept. And we can have some easy, simple simulation for this, right? For example, here I have variance that changes with time. with two frequencies, right? For example, these two frequencies, and then we have covariance, right? These are the two covariance and two variance that changes with time. So this is when Rj is 2, is a scalar number 2, and this is where the Rj is 1, 1, right? And we show that if we use our estimation, the method that I explained, you can get something. You can get the result, and both the frequency and time you can get them. The issue is, of course, like short-term Fourier transform. There are edge effect and stuff that they are trying to address, right? So, and we can actually apply this on real data, but one issue that arises here, and this is very current issue, and a lot of groups are working on this, is that it's actually really hard to show to work with high order network, right? Constructing high order network is easy, but summarizing them and visualizing them is actually really hard because the number explodes. It's a combinatorial explosion issue, right? For example, here we use a data set that uses a data set that includes two groups, again, controls and first individuals with first episode psychosis, right? It's like it's more broad than just schizophrenic. They include more individual, more type of mental disorders, right? And then again, we can run k-means on it, right? Which is a very, very easy thing to do. It's a low-hanging fruit thing to do, right? And then again, we can have a centroids, but we cannot really show the whole adjacent symmetric, right? Because it's 3D technically, you cannot show it. So what we did, just prune it and show the 10%, and we can see here that, oh, there are some triangles between 3 nodes while the edges don't survive, and vice versa, right? And then again, we have a frequency profile like the filter bank method, right? And then we can look at them both mean dual time and the length, the strength of triangle versus the links, right? And again, we can look at the links. For example, one thing that the field really likes is look at the edges, triangles, and see, oh, is the links stronger or the triangle is stronger? This has some interesting stuff because it goes back to the TDA stuff, right? Topological data analysis stuff and stuff, right? So, and so just to wrap up, right? We want, as I mentioned, the goal was building a representation of the brain, right? The goal was that, right? And originally, what the field did, and for a long time, for example, 10 years or something, we just get a brain data and build a pairwise network that is constant through time, right? But as I mentioned, this thing has many issues, right? It's linear relationship. It is between only pairs. It's pairwise and does not change with time. What we really like, and I really like to be able to build, is a kind of a unified approach that can allow us to build a network of different orders, so linear, nonlinear, and then it changes with time. And I want to have a time frequency representation too, right? So that is the unified goal, and that's what I always try to build toward, right? And build towards, right? So yeah, that's what I talked about. So these are some of the references that I mentioned. There were more. I tried to cite them in the pages, right? And these are my PhD supervisor and my current boss, and the lab that I will collaborate a lot with. And I'm always up for any collaboration or any idea that you can reach me with Faghiri@gsu.com, edu, or I'm usually always at the lab anyway too. Okay, so thank you for listening. So. Yeah.
Any questions from anyone? People online can hear. So yeah. Thank you, Ashkan, once again. Is there any questions from either the people online? We can now hear you if you want to speak up into your microphone, as well as anyone here. Any queries?
So I pick up a few points in your presentation, and I saw some ICA maps out of those correlations between different parts of the fMRI. And I wanted to know if your proposed method would change any part in ICA maps.
So ICA maps, not necessarily because that is previous to estimator that we have, but we are working on an idea that we can include those essentially try to ICA to estimate high order networks, right? Because ICA gives you connectivity too, right? Technically, right? So I didn't mention it here, but ICA themselves, the time series are actually time series of a connectivity, it's connectivity sources and the brain, right? So we are thinking about can we have a kind of high ICA so that it's high order kind of thing, those connections are high order. But the stuff that I talk here and the stuff that I usually just get ICA and I assume that okay, ICA speaks, so I'm not gonna touch that, right? Because I work usually in estimating the edges. But yeah, it can be done. Yeah.
Great.
Any other questions? If not, then I just want to thank you again for coming. I know how hard it is. Maybe I don't, but but thank you for coming anyway.
No problem.
Yeah, thank you for coming anyway, talking about everything that you're doing. And yeah,
Yes,
so
thank you for having me.
yeah, so we do not have a seminar for the next 2 weeks. Next week is because of my own fault in scheduling people, and the other week after that is because of spring break. But in 3 weeks, we have Andreas Stolk from Amazon Research Laboratories. I forgot the exact name of that company, but we'll be here. And yes, so thank you once again, and that concludes the seminar. Please eat the pizza, please drink the soda, please do what you gotta do.
Premium